Getting started. Oh, where is the keynote file? Strange. Let me do it again. Ah, there we go. Okay, is the slide showing full screen? All right, so let's get started. So what we did the last time is to take the continuum limit from the one-dimensional lattice to arrive at this expression for the Lagrangian. And this is what we call the Schrodinger field theory. So let me just review this just for a minute. So the first term tells you the canonical commutation relation between the field psi of x and its Hermitian conjugate psi dagger, and that's given by this delta function. And using the standard process of PQ dot minus Lagrangian, you define a Hamiltonian that ends up just canceling the first term and flipping the sign of the second term. So this would be the Hamiltonian you will be actually using in homework problem. And using this, we first define this vacuum state. So this state is annihilated by psi of x because that's meant to be annihilation operator. And you keep acting the creation operator at positions x1, x2, and so on and so forth to describe one particle state, two particle state, three particle state, four particle state, and so on and so forth. So all of these states basically correspond to the position eigenstates in the language of the quantum mechanics, but now you freely change the number of particles involved in the state. And so that's the main advantage we will be using as we go on. And the meaning of the word quantum field is that, first of all, psi is an operator, it's an annihilation operator. That's why it's quantum. And it depends on the position of the space. So that's why this is the field, like electric field, magnetic field, and so on and so forth. And from this Lagrangian, you can derive the Euler-Lagrange equation. So in this case, you take a variation with respect to psi dagger to obtain the equation for psi. And you can sort of see, check by your eyes how that comes about. And that actually looks like this. So this equation looks exactly the same as a Schrodinger equation for a free single particle. And that's why the resemblance of this equation to Schrodinger equation actually gave us this name called the Schrodinger field theory. But as I tried to emphasize last week, that is actually a rather misleading identification because this psi actually ends up following a nonlinear equation, as it turns out, when he actually introduced interactions among particles. So right now we are talking about a free particle. That's why the equation looks the same as a Schrodinger equation. But at the end of the day, the Euler-Lagrange equation for the field ends up being nonlinear. And for Schrodinger equation, linearity was always the key, allowing for superposition principle in quantum mechanics, and also for the purpose of unitarity, namely probability has to be conserved. And so that once you go to nonlinear equation, it becomes clear that we are not talking about Schrodinger equation, even though at this stage, it can be confusing. And I try to clarify that point in multiple times as we go on. So anyway, this is what we did last week. So we actually go from here. But anyway, so let me pause here for the moment and see if you have some questions about what we have been doing so far.
Professor, could you repeat why this is not linear?
This is linear. So, and this is linear because we're talking about the free particles so far. But we will introduce interactions among particles later on. Then you find actually another term that describes the interaction, and that term is actually nonlinear. So at this stage, it's still linear, and so you're pointing that out right now, which is good. But later on, you will see that this equation turns into a nonlinear equation, and that's why it cannot be the Schrodinger equation. So interpretation will be different. Thanks for asking that question, Chirag. Any other questions? Okay, so let me move on. So you have seen quantum field theory now. So let's see how we can actually put that to use. So again, the same stuff over here. And now I'm forming a linear combination of this state, psi dagger x acting on the vacuum state, which is a state with a single particle localized at position x. So now I'm forming a linear superposition of that state because I'm integrating over x, so that's a linear superposition, with a weight given by this plane wave factor e to the ikx. And again, you are looking at this state in your homework problem. Well, let's see how this works. So the idea is that I act the Hamiltonian, which is integrated over space. And to avoid the clash of notation, I'm going to actually switch the position of the Hamiltonian to be y instead. It's a dummy variable for integration anyway, so I'm freely allowing myself to change the notation from x to y, and so that this y doesn't clash with the notation x over here. So here, I'm literally just acting a Hamiltonian operator on the state I prepared. So let's see how this actually works out. So the idea is that this psi dagger creates a particle on top of the vacuum state. But if you follow the order here, then this psi would annihilate that particle. So you go back to zero particle state. And then you create a particle again so that you end up still being a one particle state after acting all of these operators. And psi being an annihilation operator, if I replace this del y psi y and psi dagger x with a commutator. Commutator has a piece that, of course, has the opposite ordering between them, so that psi dagger is on the left and del y psi is on the right. But when psi touches the vacuum state, it annihilates it, so it does not contribute to the end result. So switching from this operator to the commutator, I have not changed anything because I basically added -0. So I'm allowed to change it to this commutation relation. And you're going to actually use this trick over and over again whenever you're dealing with a quantum field theory. So this is a useful thing to remember. But now that this is a commutator, I can use this canonical commutation relation. So this del y is a derivative acting on psi. It's not meant to be a quantum operator. So I can take this del y out of the commutator. And if I take this out, the rest is psi dagger commutator. That's precisely this canonical commutation relation. So that's given by this delta function right here. And remember, this y derivative was supposed to act on y inside this field that turned into a delta function. So this y derivative is now acting on this delta function. But the delta function, of course, has no terms at the spatial infinity. So I can do the integration by parts without any boundary terms. So I let this derivative on respect to y act on this psi dagger instead, of course, by changing the sign. So there's an over minus sign up front. Now del y squared acts on psi dagger. And then I have a delta function. And using this delta function, I can integrate it over y, and y is replaced by x everywhere. So I end up with this expression down here. So now it has gotten a lot simpler. Then once again, I'm allowing myself to do the integration by parts, letting this x derivatives act on this x in the plane wave factor over here. So del x will pull out ik from the exponent. So I have ik twice, so that's negative k squared. A negative sign cancels the negative sign up front. So I end up getting this h bar squared k squared over 2m. And the derivative is now gone because I already used it acting on e to the ikx to pull out k. So now you see that this number, h bar squared k squared 2m, is just a number independent of x. I can pull this out. So the rest actually turns into dx psi dagger x acting on the vacuum state together with e to the ikx. That was the definition of this k state to begin with. So this is how you can verify that this state I constructed over here is actually a Hamiltonian eigenstate. And the meaning of state, I believe, is pretty clear. Oops. Namely that this is the state with energy being the eigenvalue of the Hamiltonian, and h bar times k the h bar times wave number is the momentum of a quantum particle. That's a de Broglie's relation I'm sure you have seen in quantum mechanics class. And the energy then is p squared of 2m. That's exactly what we want for a point particle of mass m and momentum p. So this starts actually giving you better intuition on what's going on. So it's really the case that psi dagger x acting on the vacuum state has a meaning of a position eigenstate x. And if you take a linear superposition of the position eigenstate with this wave factor on top of it, that is basically the Fourier transform to go from position space to momentum space. And I hope you have seen that in quantum mechanics class. So this one literally has this meaning of the momentum eigenstate by construction. And therefore, the identifying this psi dagger of x acting on the vacuum state really does have the meaning of the position eigenstate like in quantum mechanics. And of course, the language is different now, but it's describing the same thing, exactly the same thing with exactly the same energy. So this is the place where you're beginning to see, I hope, a little bit more intuitively what's going on. And you can compare what we are doing with the QFT to what you're familiar with from quantum mechanics and sort of set up a dictionary in your mind, how they're related to each other. So that's the beginning of this discussion. So any questions about this slide? I see a chat. Can you mention why we pick up the minus sign again? Yep. So this minus sign came about because I'm using integration by parts to let this derivative with respect to y acting on this one. Then integration by parts, of course, give you a minus sign, and that's the origin of this minus sign. At the same time, when I act this derivative squared on e to the ikx, I change the sign twice, so it stays negative sign up front, but each derivative will pull out ik from the exponent, so I get I times k twice, so that multiplies to negative k squared, so that negative sign ends up canceling this negative sign so that I have a positive sign at the end of the day. Does that answer the question? And let's see, who was it? Good, okay. Thank you, Daniel. Any other questions?
I did have a quick question. You said you factored out the derivative from the commutator. Is that what you said?
Mm-hmm. So at this step, right?
Yeah.
So this derivative, you can say that's an operator in the sense that it does do the differentiation, but it's not in the sense of the quantum operator. So the psi and psi dagger are operators, and they satisfy this commutation relation. But y derivative is basically acting on just psi of y. And so I can let the psi derivative, y derivative acting from outside this commutator. And so that's not going to make any difference between the two. So that's what I meant that I pull out this y derivative outside the commutator because it's meant to act on psi only anyway. Does that answer your question, Geraldo?
Yeah, I think so. Yeah.
Okay, good. Anything else?
So when you do integration by parts, why does the first integral go to 0?
A first integral, which one are you referring to?
So when you, in the step where you do integration by parts.
Mm-hmm. I did it twice, here and there, okay.
Okay, yeah, the first time you do it, or not the first integral, but the first term that you get from doing integration by parts, why does it go to 0?
So boundary terms, I'm actually dropping boundary terms. And as we talked about before, the simplest thing to justify dropping the boundary terms to assume a periodic boundary condition so that there's no boundary. So that's the simplest way of justifying it. Okay, any other questions?
Yeah, I had a quick question. So in the step where you insert the commutator, usually when you do that, so it's like the product of del psi y and then psi dagger, but like in the commutator is like the difference of like
two different orderings.
Two products.
Right.
So there should be a second term, right?
Yeah,
Is that
the second term actually vanishes because the
okay?
second term has this psi on the right, psi dagger on the left. Then the psi acts directly on this vacuum state
Oh, okay.
and
Yeah.
get annihilated. Yeah, so second term is just identically 0. So I have just
Okay,
added
yeah.
0 from the first line to go to the second line. Good. Any other questions? All right. So I'm hoping that things start to make sense, even though this is a new language for you. So what I'm just telling you is that this is one-to-one correspondence between what you do in QFT, this is this state, versus what you do in quantum mechanics. So I believe you have seen this decomposition of unity, namely if you use this complete set of states, in this case in position representation. So this dx, x cat, x bra is inserting the complete set of states. So this is actually identically 1. So from the first expression to middle expression, I have not changed anything. But as you know, the x bra times k cat is basically the wave function of the momentum eigenstate k. And so this wave function is the plane wave e to the ikx. And depending on the convention, sometimes you have the over normalization factor, like 1 over square root 2 pi h bar and stuff like this. So here I'm not so much worried about the over normalization factor, just in case that you're wondering about it. But the whole point is that this xk inner product is nothing but e to the ikx. So if you compare this QFT language and the QM language, you can really see this one-to-one correspondence between this state, psi dagger of x acting on a vacuum state, to this position eigenstate x cat, which is the literally eigenstate of the position operator. So there's this one-to-one correspondence between QFT and quantum mechanics. So this is where you can start to see that QFT, Schrodinger field theory, has identical physics content as the quantum mechanics, but it's bigger. And as I emphasized many times, the QFT language allow you to talk about 0 particle state, 1 particle state, 2 particle state, and so on and so forth in the same big Hilbert space. On the other hand, in the case of quantum mechanics, Hilbert space is defined specifically for a particular number of particles you got in the system. So each time you have to start from scratch, building the Hilbert space and describe whatever physics you would like to describe, and you can never change the number of particles. So as you will see later on, the second half of this course, you get to see photon. Once we incorporate relativity into QFT, then you can describe the process where you can emit a photon from, for example, atomic excitation. You can absorb the photon, you can scatter a photon, and those processes would require this big Hilbert space in which you have states with different number of particles in it. And you can freely move back and forth and change the number of particles. So you would literally be talking about creation and annihilation of particles, as the name suggests, from the creation annihilation operator. So you see the beginning of it. And in the case of this 1 particle state in QFT, now you can see this one-to-one correspondence between the two. And so, as I said this already, so xk in a product is nothing but this plane wave factor that is common to both languages. And so that's the one-to-one correspondence. And you can think about going to a more number of particles too. So if you have 2 particle state, this psi dagger x1, psi dagger x2 acting on this vacuum state is 2 particle states. 1 particle is localized at position x1, second particle is localized at position x2. And once again, I'm taking linear superposition of these localized states by this the plane wave factors. And you can go through the same exercise as we did before, and you can confirm yourself that this is also a Hamiltonian eigenstate. And as you would expect, it ends up the sum of 2 kinetic energies of 2 particles with momenta h bar k1 and h bar k2. So here you again confirming the interpretation that this is a 2 particle state of 2 free particles. So quantum mechanics way of describing the same thing is to define this ket with two particles with wave vectors k1 and k2. Once again, I use this complete set of states with x1, x2 integral. And this inner product between x1, x2 and k1, k2 ends up being this e to the ik1 x1 times e to the ik2 x2, except that you can also have the opposite order between these two particles, which is given by the second term e to the ik1 x2 times e to the ik2 x1. And in the case of QFT, you don't have to do it because two side daggers commute with each other. So this wave factor, even though it looks like K1 is specifically associated with X1, K2 specifically with X2, but remember X1, X2 are just the dummy variables of an integral. I can switch X1 and X2 and then commute them over. Then I recover the same state, except that K1 gets now associated with the X2 instead. X2 is associated with X1. So interchange of two particles is already built in, and it's automatically symmetric with respect to interchange of two particles. But in the case of quantum mechanics, you have to do this by hand to add the second term to make sure that it has the right property. So in the case of quantum mechanics, that writing it this way, you don't necessarily know whether two particles are identical particles or non-identical particles. But in the case of QFT, both of them are created by the same field operator of psi dagger. So they are identical particles. So the symmetrization is already built in to this formulation. On the other hand, in the quantum mechanics case, you have to tell this definition of the state that you meant them to be identical particles. And when you mean it, then you have to actually do it by explicitly symmetrizing the wave function by adding the second term. And so that's the difference between QFT and QM. Namely that in QFT, if multiple particles are created by the same creation operator, they are meant to be identical particles from the bat. And therefore, the wave function comes out to be automatically symmetric under the interchange among them. But in the quantum mechanics, you have to do it by hand to force the state to describe identical particles by explicitly symmetrizing between them. So that's already a one advantage the quantum field theory has compared to quantum mechanics. So multi-particle quantum mechanics of quantum statistics is built in to the quantum field theory. So I went from one particle state now to the two particle state, but I hope this dictionary is still clear to you. So this state of using two creation operators acting on a vacuum state is meant to be the same as the quantum mechanics state of the two particles in position eigenstates x1 and x2. And you see the same wave factors in both cases. The only difference is the explicit symmetrization you have to do by hand on the quantum mechanics side, but you don't have to do it on the quantum field theory side. That's the only difference between the two, and they have identical physics in it. Okay, let me stop here again to see if there are any questions.
So could we act two different creation operators on a state, and then those would not be identical, and they would be fermions, I guess? So they would need to be antisymmetric?
So we're going to talk about fermions later on. It turns out that in the case of fermion, instead of this canonical commutation relation, which goes for like AB minus BA, we'll be talking about anti-commutation relation that looks like AB plus BA. So if you have AB plus BA, by moving one term to the other side of the equation, you get a negative sign. And that's how you know that interchange of two particles end up giving you a minus sign, and hence antisymmetrization of the multi-particle wave function. So you're going to see that later on.
Okay, thanks.
Thank you for the question. Anything else? All right, so let me move on. So here, I hope the dictionary is now sinking into your mind. And whenever you have some arbitrary state, and here I'm using the symbol capital psi to represent the state, because I want to distinguish notion of the state from the notion of an operator, field operator, a lowercase psi. This is uppercase psi. So I describe states using uppercase psi and field operator with a lowercase psi to avoid a potential confusion here. And if you go to multi-particle quantum mechanics, I can once again use this complete set of states for n particles. And so I'm inserting this the position eigenstates and add over them so that this is just the unity, decomposition of unity. And then this X bra is an inner product together with the state psi. And that's the meaning of the wave function in quantum mechanics, right? So the wave function of quantum mechanics is the inner product of a psi state in the position eigenstates. So this is the meaning of the wave function. So wave function is meant to be smeared over all the positions using this position eigen ket, and that defines the original state ket psi. So the wave function is supposed to be a weight on this position eigenstates when you actually write it this way. So in the same way, in QFT, you do the same thing. So we made this dictionary that this position eigenstates for n identical particles correspond to the n creation operators acting on the vacuum state. So this x ket is now replaced by this psi dagger multiple times acting on the vacuum state. Then this weight function, capital psi, that's the wave function in quantum mechanics language, is just again the weight function in smearing over all the possible positions a particle might occupy. And so once again, they are in one-to-one correspondence. So this position eigenket of n identical particles is what corresponds to this n creation operators acting on the vacuum state. And you can describe whatever state you like for a given number of particles as a linear superposition of these position eigenstates. And the weight you provide to take this linear superposition is nothing but the wave function in quantum mechanics. And now comes an important test. So if this interpretation is correct, namely that this weight function capital psi is indeed what is supposed to give you the wave function in quantum mechanics, then this weight function capital psi is supposed to satisfy the Schrodinger equation you are familiar with from quantum mechanics class. And this is now a non-trivial test. Now there's no wiggle room because we know what the Hamiltonian is in QFT, written in terms of field operator. I used 2 slides ago, right? So we have the Hamiltonian. Now we have a state. Then I can write Schrodinger equation in QFT to figure out how this weight function capital psi changes in the course of time. And if that equation turns out to be identical to the Schrodinger equation back in quantum mechanics case, is a non-trivial test. As I said, there's no wiggle room. If they don't agree, we are dead. Then this theory doesn't work. So we have to make sure that that is the case. And no, that is not the case. I misspoke. And if it's not the case, then of course there's no point taking this class, right? So we'll see if this weight function capital psi really does end up satisfying the Schrodinger equation with the Hamiltonian we used over here in the case of single particle. But now we'd like to do this for the multi-particles too. And if they agree, then that will confirm all the intuitions we came up with in how to identify what's going on in QFT in terms of what you are familiar with in quantum mechanics. And you can see this is taking a long time because I intentionally slowed things down for the purpose of not speaking too fast. Okay, finally seems to be getting there. To the next slide. Ooh, still more way to go. Okay, I'm sure this is the last one. There. So we would like to confirm this dictionary that the creation operators acting on the vacuum state literally does describe this multiple particle states in the position eigenstates by working out the time dependence of this coefficient function psi x. And if that they agree with each other, and then you get a sort of confirmation that what we are doing really doesn't make sense, and the physics is the same between quantum mechanics and quantum field theory. It's just that they rely on a different formulation of the same physics. Even though it's the same physics, we still do like to have the formulation of quantum field theory because one, I said already, quantum statistics is built into this. And second, eventually we would like to describe processes or states where different number of particles would come together within the same Hilbert space. We end up needing a state like that when you describe the superfluidity, the superconductivity, and also the particle emission and absorption later on. So switching to QFT makes sense because there are certain things you cannot do in quantum mechanics. Namely, you cannot talk about the states with different number of particles on the same footing within the same Hilbert space. That's why we prefer to go from quantum mechanics to QFT by making sure, to the extent we're describing the same physics, they are identical. So that's the idea. All right, let me stop here again to see if there are any questions. So is this idea of the decomposition unity using the complete set of eigenstates, is that okay with everybody? Okay, good, good. Any questions? All right, so let's try to confirm that. So we have this Euler-Lagrange equation for field psi. And this looks like a Schrodinger equation from this Lagrangian. But as I said already, it's not meant to be that. And from the Lagrangian for point particle, you obtain the Schrodinger equation by replacing the momentum by the derivative operator acting on the wave function. That's something you are familiar with. And so some people call this, from historical reasons, as the first quantization, where this psi first appears. And then you promote this to a Lagrangian made of psi and quantize it again to obtain quantum field theory. So that's how the people came up with this name called second quantization. But as I tried to emphasize already last week, this is definitely the wrong name. It's a misnomer, and it's actually a misleading, confusing name. Because, you know, there's no second quantization. We go from classical physics to quantum physics only once. And so the fact that this multi-particle state is supposed to have the same physical meaning as the multi-particle state in quantum mechanics is a way of making sure that quantization is done only once. You go from classical description to a quantum description. Your starting point is now different between quantum mechanics and QFT. Starting point in quantum mechanics is that you start with a Lagrangian of a point particle. In QFT, you start from the Lagrangian made of a field. So that's the difference. But it's still the same that you do quantization only once to go from classical theory to the quantum theory. And in the case of description using the particle in quantum mechanics, you start with particles, you quantize it, and you get a wave function. And that's how you find this particle wave duality, which is the most bizarre thing about quantum physics. And what we are doing here is sort of the opposite. You start with a Lagrangian made of waves, you quantize it, and then you find psi to become an operator instead of classical wave, and then you find particles coming out of the theory. So you go from wave to particle to describe the same particle wave duality, but it's meant to be the same thing because quantum object is never really a particle or really a wave, and we are doing it just for the convenience for us. We mere mortals don't have a good intuition of describing this object, which is both particle and wave to begin with. So we have to start somewhere, And in quantum mechanics class, we chose to start with particles and introduce wave. But you could have started also wave and quantize it to obtain particles, because either way, you are trying to describe an object which is both particle and wave at the same time. It's just that the starting point is now switched, but it's the same physics. So that's why this idea called second quantization is a wrong idea. And I emphasize that we are doing quantization only once for all. But when you do quantization once for all, you find this weird object, which is simultaneously wave and particle. And that's exactly what quantum physics is supposed to be. So we are doing this formulation for the convenience of us mere mortals who don't have a better intuition than doing it this way. But either way, we are supposed to be describing the same physics. So that's what this slide was meant to convey. So this is sort of the conceptual issue. So I'm sure you got questions about this, because conceptual issues are always more difficult to sink in compared to sort of technical manipulation with the operators and stuff like this. So please ask questions on that. Is everything clear? Sure. Okay, anyway, so this idea, of course, oh, go ahead, Ju.
Yeah, so here there is an arrow in front of the Lagrangian of psi comma psi dot.
Mhm.
But that
So, yeah.
arrow shouldn't be there, right? That's just the starting point in QFT.
That's right. But this commutation relation is, you said starting point, but this is actually derived from the Lagrangian. So that's why there's an arrow. So once you have this Lagrangian at the top of this slide, the first thing you'd like to do is identify canonical momentum to the variable you have. So variable of the Lagrangian here is psi, and canonical conjugate momentum is obtained by taking derivative of the Lagrangian with respect to the time derivative of the variable you have. That's psi dot. So psi dot derivative of the Lagrangian is IH bar psi dagger. So IH bar psi dagger is basically Q, and psi is, the P, and psi is X in quantum mechanics. So that's how you end up with canonical commutation relation between X and P here. So psi over X is what corresponds to X in the particle mechanics. IH bar psi dagger is what corresponds to P in particle mechanics. And commutation relation is supposed to be IH bar. So I have canceled the IH bar from both sides, and that's how derive this canonical commutation relation. So this is actually not God-given. The Lagrangian is the starting point, and you derive the canonical commutation relation. And once you have canonical commutation relation, you know how to build the Hilbert space by keep using this creation operator on top of the vacuum state. So that's the idea, and that's why I'm using an arrow here. So this is not the starting point, but this came from the Lagrangian we got up here. Does it make sense, Ju?
Okay. Yeah, that makes sense. So the starting point is Lagrangian of the psi and psi dot, right? Okay.
That's right.
So it's not coming from Lagrangian of X and X dot.
No. So
Okay,
in some sense, what we are trying to communicate here is that this arrow should be removed. This is not second quantization. Yeah. So Lagrangian point particle would lead to the standard Schrodinger equation. Lagrangian of the field would lead to this commutation relation, and hence everything else follows: Hilbert space, the time evolution of states, and so on and so forth. So in either case, Lagrangian is the starting point. You quantize it once, and everything else follows. So this arrow is what some people refer to as the second quantization, but this is wrong idea. That's what I'm trying to say. I hope that makes sense. Okay.
Yeah.
Good. So maybe I should post the slides again by removing this arrow to make the point clear. Any other questions?
Yeah.
Go ahead.
What is quantized in the first quantization? Isn't the arrow just the principle of least action from the
Yeah, that's right.
Lagrangian?
Yeah. So here you see a disparity between the two because I just omitted it. So from the point particle Lagrangian, then x dot appears in the kinetic energy half mx dot squared, right? So from that, you identify the canonical conjugate momentum by taking the derivative of that with respect to x dot. So P, therefore, is mx dot. And that P is supposed to satisfy canonical commutation relation, xp being IH bar. So I skip that step in here. But this xp being IH bar is the reason why you can replace P in the Hamiltonian by H bar of I del X, right? So if you go from Lagrangian, first thing you derive is the canonical commutation relation. Canonical commutation relation allows you to identify momentum operator with the derivative operator with respect to x. And once you know that, you can write down the Schrodinger equation and discuss energy eigenstates, time evolution, and all that stuff you have seen in quantum mechanics. And I'm just describing the first step of that. From the Lagrangian, you derive the commutation relation, and that allows you to talk about states and Hamiltonian and time evolution and everything that follows from that point on. So that's why they are totally analogous to each other. Does that make sense, Asha?
Yeah. Thank
Great. Anything else?
Yes, Professor. What? Um, why are we using the psi dot but also the del? What makes the difference between those? Is the del a derivative of x?
Yeah, the del is the derivative with respect to space. And so far
Okay.
we are talking about one dimension, but we can certainly generalize as 3 dimensions. It's always referring to space. And dot, according to Newton, is always time derivative.
Okay.
So if you
That's
don't like it, blame Newton, don't me, okay? And then you can
Okay,
call me
thank you.
Hitoshi, Andy. I prefer it that way.
Okay. Okay, thank you.
Okay, any
Hitoshi.
other questions?
So with regards to even making up the creation and annihilation operator, we had to assume that there was a simple harmonic oscillator at every point within space. Is that an assumption that is justified later, or?
Yeah, so in some sense, what we're going to do right now is what would justify it, because we started out with creation annihilation operator at every position in space, and then took the continuum limit, then arrived at this Lagrangian. So if this Lagrangian and Hamiltonian would lead to the same time dependence for this coefficient function capital psi between quantum mechanics and QFT. And that is the verification that we have done the right thing. So in some sense, using harmonic oscillator was a simple guess, but that actually turns out to be proven right that way. I hope that argument makes sense.
Yeah, it makes sense. Taking the result, seeing if the result looks all
Yeah,
right.
that's right. So in some sense, I'm taking a sort of heuristic approach. I could have actually started with this Lagrangian and could have told you, well, this is what you're supposed to take it seriously. And we derive everything from there. And that's sort of top-down approach. But I kind of hate it, being a physicist, we always start with phenomena and trying to write a theory for it. So, what precedes is always something we know. And what comes out of it is the theory we like to build. So I'm trying to go that way. So what we know is quantum mechanics, but we have a need to describe processes where number of particles can change and so on, and quantum statistics are built in and so on and so forth. So we are starting with quantum mechanics as an input, and then try to build quantum field theory out of it. And so that's the line of arguments I'm following right now. And this argument is not in the textbook, but I believe this actually make a better sense, and so that you get an idea what's going on and why this is supposed to be a good idea at the end of the day. So that's the idea of my discussions here. Thanks for asking the question, Earl. Anything else? Good. So now we would like to confirm this. And in order to do so, it's actually useful to introduce interactions. And this is exactly what we're missing these days. And I really miss, in-person interactions with my colleagues and students and postdocs. Hopefully we get back to it in the fall. But anyway, so we introduce interactions among particles here, not among people. Okay, so in terms of talking about interaction, one way you can introduce interaction is to put particles in some external potential. So suppose this one-dimensional space has some kind of potential energy, like Coulomb potential in the case of atoms, and then each particle is supposed to be moving inside this potential. So that's one step we can improve on what we have done so far. And what we know is that the free particles seem to be described by this Lagrangian we already introduced, again, back to this discrete space. And we are putting particles in this potential. So whenever place a particle at a given location, that is supposed to come with the potential energy at that location. So what that means is that if you have particle at this position 5, I'm supposed to get extra energy, namely negative Hamiltonian, so in the Lagrangian, associated with this potential at a given position. And the same for the position 6, same with the position 14. So I'm supposed to add this term now, namely that when you have a particle at position n, A dagger A is a number operator that gives you 1 if you have one particle at the position. And for the particle at that position n, you get this extra contribution to energy from the potential energy at that position. So this is the way I can now introduce interaction to the system when these particles are moving in a potential. So the Lagrangian contains this negative or Hamiltonian. So this thing here actually turns out to be the Hamiltonian. And you can even place a particle twice, 3 times, and so on at a given spot, at a given site, and it's one dimension. And if you have 2 particles at position 6, then A dagger A is the number operator, and this state has eigenvalue 2 for this this state, and therefore I get twice the contribution of this potential energy, and that's exactly right. If you have 2 particles at that position, then total energy of the system would come with the potential energy at the position twice. So that's how this whole thing, I believe, would make sense. And so that's how we can actually introduce this external potential to the description. So in the case of the second state, I have twice the contribution of the potential energy at position 6 instead of position 5 and 6. So I just move this particle to 6. And so the only thing that changes in this case is this the potential energy. And because we have gone through the taking continuum limit already once, I'm not going to actually repeat this in gory detail. But once you actually take this identification and they take the continuum limit so that the difference turns into derivatives, and of course, I'm not writing this hopping term here, but it's meant to be there, then end result looks like this. So this V at a particular site turns into V of X now on continuum space. And A dagger A at the particular site turns into psi dagger psi at the position X. So this is just the continuum limit of the idea we just talked about. And then you can derive the Euler-Lagrange equation from this Lagrangian, and you find this. So what you see is that this is still linear, and it still looks exactly the same as the Schrodinger equation. So we haven't resolved this confusion fully yet. It turns out that what is missing now is the self-interaction among the particles. So what I introduced now is the particle interacting with external potential given by something else. So it's not internal to the system, it's an external potential provided on the system. But if you talk about internal interaction, for example, in this case, 2 particles at the same position. Imagine they actually repel each other. Then this state should come with higher energy than this state, because here they don't repel, here they do. So taking two particles at the same position should cost you extra energy if they repel each other. So there should be yet another extra term on top of this that will represent this idea that these particles would interact among each other. That's a self-interaction among identical particles. And we need to introduce yet another term to the Lagrangian to be able to describe that possibility. And once you try to do so, it turns out that would introduce nonlinear term to this Euler Lagrange equation. And then you will see, aha, certainly this is not a Schrodinger equation. So that's the way I'm going to proceed from the next slide on. Okay, let me stop here again to see if there are any questions. Is it okay how to introduce the external potential?
I have a quick question. I think I just
Go ahead.
need, reminding on the potential term where it's V. There's a n dagger a n term. And I think that a dagger and a n term. Why is that there? Why do we need to destroy the create to get the potential?
Yeah. So I'm supposed to act this Hamiltonian on either of these states, right? So this cartoon describes a state where I created particles at position 5, 6, and 14 on the vacuum state. And same here, I created two particles at position 6 and one particle at position 14. So these cartoons represent a state. And I act as Hamiltonian on that state. And what I want is to extract potential energies for each of the particle I got in the state. So when I use this an dagger an operator, and this is summed over n, so it contains a piece that goes like a1 dagger a1, but a1 acting on state would give you 0 because I have not created a particle at position 1 yet. So that's 0. Same for a2 dagger a2, because I have not created a particle on side 2, that also gives you 0. And I keep summing it until the point I come to 5. Then a5 dagger a5, acting on this one particle state, gives me 1. So I get the first contribution that gives you V of x at 5d. So that's this potential energy I wanted to have. And same with a6 dagger a6, I again get V6, and that's something I wanted to have. If you move up to 7, there's no particle here, so a7 dagger a7 would annihilate the state, so no contribution. Same with site 8, site 9, ... And when you get to site 14 in this sum, then a14 dagger a14 gives you 1. So I get a contribution to the energy given by V evaluated at position 14, and no contributions from 15 on again. So that's why this an dagger n was needed to make sure that you get contribution only when you have a particle at the location. And if you have two particles at the location, you get the contribution twice, and that's exactly what you need for this state too. So that's why I need to have this a dagger a in this sum over n. Does that answer your question, Geraldo?
Yeah, it checks if there's a particle there first, and if there's not, just skip it. And then, okay,
exactly.
Yeah, that does make
That's
sense.
the idea. Yeah. Anybody else with a question?
I have a question.
Go ahead, Natalie.
So how do I put this? So the energy weighting. So if you have two particles, you have twice the energy. That makes sense. But how does that relate to how we call the capital psi, the wave function in position space? How does that relate to the fact that we're calling that a weighting as well?
Yeah, so you will see that more explicitly as we move on, because we're going to actually act the Hamiltonian in field theory together with the potential term, and also together with self-interaction I'm going to introduce next, to see that this capital psi does obey the Schrodinger equation, including the external potential and self-interaction. So that's how we're going to actually verify that. So that's exactly where we're heading to.
Okay.
Okay, thanks for the question. So that everybody knows where we are going. Anything else? Okay, let's move
Can
on.
you quickly?
Oh, go ahead.
Sorry, can you quickly just show how if you have two particles at the same location, say at 6, how that reduces to 2 times the energy? I'm just the math is just not.
Yeah. So this picture tells you that I used creation operator at position 6 twice, and creation operator at position 14 once on the vacuum state, right? So in terms of the particle here, this is in state 1, and here is in state 2. And AN dagger AN is a number operator at that location. So A dagger AN has an eigenvalue 2 when N happens to be 6. So that's how you get this contribution twice. Okay, thank you for the question too.
Okay.
Yeah. Anything else? Okay, let me move on. So far, the Euler-Lagrange equation still looks linear and looks like Schrodinger equation, but I promised you that it would end up being different at the end of the day. So how do we introduce repulsive interaction? So what we want is that in any of these first 4 states, the particles at a different location, let's assume that repulsive force is very, very short range. So as long as they are separated on different sites, you don't see any repulsive force. So that's an assumption I'm making for now. So the only case you do see a repulsive force is when 2 particles are at the same location, and that should cost us extra energy. So that's the way I'd like to describe a repulsive interaction. So the question is, how do we describe that using this language of the creation annihilation operators? So the difference between states where all particles are at different locations and a state where some particles are the same location is really just this label for the creation operator. So we need to find a way of picking up the label when they are at the same location. And by going from 0 particle to 1 particle, so this Lagrangian tell you that it costs you energy h bar omega. Here, twice h bar omega, 3 times h bar omega. This state also has only 3 particles. So at this level, you get 3 times h bar omega. But I want to get this extra repulsive potential U on top of that. And to get this extra term, what I'm supposed to do is add this term. So what's going on here is that this annihilation operator and creation operator are at the same location N. And when you act this operator on the state, you are trying to annihilate particle at the location N twice. So if there's only 1 particle at this location, then first annihilation operator would bring 1 particle state to 0 particle state. And the second annihilation operator would act on the 0 particle state. And then that would give you 0. So this term does not contribute when you have only 1 particle at the given location N. But for the last state, I put 2 particles at the same location 6. So in terms of position 6, this corresponds to harmonic oscillator state 2. And state 2 can be lowered to state 1 with 1 annihilation operator with the coefficient square root 2. Second annihilation operator would bring the state 1 to 0 with a coefficient 1. So this doesn't vanish anymore. Then I create operator particle again, starting from 0 state to 1 with coefficient 1. And from 1 to 2 with the second creation operator with a coefficient square root 2. So I get square root 2 twice. That cancels this 1/2. So that I get this additional contribution U. Remember, Lagrangian has the negative of the Hamiltonian, so this minus sign corresponds to plus U, and hence the repulsive force. So adding this term in the Lagrangian achieves this goal of describing a repulsive potential energy among identical particles when they happen to be at the same location. And to describe that, I need an operator that includes two annihilation operators to make sure that it picks up contribution only when two particles are at the same location, and bring it back to the original state by using two powers of creation operator. And now we have a piece in Lagrangian which has two A's and two A daggers, which is different from the other terms I had, which always had only one A and one A dagger. Now you see, if you take the variation with respect to A dagger and write down the Euler-Lagrange equation, this term, I take the variation with respect to A dagger, this term gives you a term in the Euler-Lagrange equation that has one A dagger and two A's in it. So then it's no longer linear, and you find a non-linear Euler-Lagrange equation. Then you know, Euler-Lagrange equation is definitely not the Schrodinger equation. It looks sort of similar, but that was in some sense just a misleading fact. So it was a fake news. And the true news is that the Euler-Lagrange equation is not the Schrodinger equation. And that's what we're going to see in a minute. But I hope it's clear that using this term here is a way of describing the repulsive interaction among particles when they overlap at the same location. I'd like to be sure that you get this idea of this cyan term. So any questions about that?
What if there are three particles in one state?
Yeah, that's an excellent question.
Would we have like three annihilation operator and 1/2√2?
That's right. So if we have a three-body interaction, namely that if particles interact only when you have three of them together, then you can use an operator with three annihilation operators and three creation operators. So you got exactly the right idea. You can ask also a different question. What happens if I place three particles at the same location and use this operator? Then you have a state 3 at this location. You lower it once, that gives you square root 3. You lower it again, that gives you square root 2. And square root 2, square root 3, I get a factor of 6 divided by 2. So I get 3u in that case. But that also makes sense. So the idea here is that two particles coming together would cost you energy u. And if you have three particles at the same location, this particle 1 and 2 has a repulsive potential u. Particle 1 and particle 3 has repulsive potential u. Particle 2 and particle 3 has repulsive potential u. So altogether, you are supposed to get 3u from the repulsion, two-body repulsion for three particles. And that's exactly what you get from this operator. So it works out. So what this is describing is the repulsive force among two particles. And when you have three, then you have three choices. When you have n, you basically have to choose n2 choices. And that's exactly what you're going to get from this operator. And you can verify that. But if you want to describe a three-body interaction, namely two particles coming together doesn't give you any repulsion, but only when you consider three particles, they repel, then you use a different operator from this one using three creation operators and three annihilation operators, exactly as what you suggested, Natalie. Does that answer your question?
That makes sense. Yeah.
Okay, good.
I have one more question.
Go ahead. Yeah.
So in this case, we're looking at like, so when we look at a continuum limit, how would these interactions convert, I guess? Like,
yeah. So we will do that on next slide. So you will see it.
Okay.
You're ahead of me. And Ju, you wanted to ask a question too. Ju?
Yeah.
That was Ju. It wasn't Natalie, it was Ju. I was asking that.
Oh, I'm sorry. I misread the name. Apologize. Good. Any further questions at this stage?
Is it non-trivial that it works out really well for the three particle case, or is it does it all make sense?
It is again built in with this language. So if you start with the state n, first annihilation give you square root n, second annihilation give you square root n minus 1, and square root n minus 1, square root n. So you get n times n minus 1 over 2 is n choose 2, right? So
Yeah.
you can see explicitly that that is indeed the counting the number of pairs which will
That
repel
makes
each
sense.
other.
That makes
So it precisely
Thanks.
comes out that way. And that's another verification that using this harmonic oscillator is really the right way of describing the multi-particle state. It seems non-trivial to me, at least.
Yeah, yeah.
Okay, any further questions?
Oh,
Okay.
I have a question.
Oh, go ahead.
Professor.
Go ahead. Yeah.
Will we see how to construct a model like this for fermions also?
Yeah, we will discuss that for fermions too.
Okay.
Yeah. So here I'm just repeating the explanation I said verbally. So for the one particle state, using two A's, that identically vanishes. But for two particle state, the first one pulls out square root 2, second one gives you only 1, and the first one, creation operator gives you 1, and second creation operator gives you square root 2, so that you get a factor of 2 overall that cancels the factor of 1/2. So I'm just writing it down. I forgot that I actually did. So this piece is indeed the Hamiltonian with the right idea of describing the repulsion among particles. So we take the continuum limit again. The sum over d goes to the integral dx thanks to Leibniz once again. And we made this identification that the annihilation operator should be given in terms of this continuum field with a factor of d to the 1/2. And if I do this, I pull out 4 powers of d to the 1/2. So that gives you d squared. 1 power of d turns into the integral. So I'm still left with another power of d. So I have to assume that when I take the continuum limit, I keep this product u times d fixed. And that sort of makes sense, right? Because we're talking about the localized interaction. When you go to continuum limit, correspondingly, you need to make the size of the repulsion bigger so that overall force you get remains constant. So I take this product fixed. And so I just introduced a new symbol for UD, which turns into the Greek letter lambda from the next slide on. But here I'm just verifying something I mentioned also on the previous slide. From this Lagrangian, I can derive the Lagrange equation for the field operator by taking variation with respect to psi bar. So the first term gives you this. Second term, again using integration by parts, give you this. But the third term, taking variation of psi dagger, there are 2 of them, so I get a factor of 2, that cancels 1/2, I get just UD. But the point here is that I took the variation with respect to 1 of psi dagger, the other one remains. Psi's, I didn't take variation, so they all remain. Then you find this nonlinear term. So this is the first time you see explicitly that the field operator is not the wave function, because it follows a nonlinear equation. Wave function needs to satisfy the superposition principle, as you have seen in quantum mechanics class. So the Schrodinger equation has to be linear, but this equation is nonlinear. That's how we know psi is not a wave function. It is really a field operator. And of course, we know that already by now, because psi is meant to create particles. It's not a wave function. But now you see the clear distinction between these two ideas, between the Schrodinger equation that has to be linear versus field equation, which may be linear too, but it can in principle be nonlinear when the particles have self-interaction. So regarding this as the first quantization is clearly a wrong idea. Now you see it very explicitly. So they don't regard this to be second quantization, even though people talk about this name in the literature. It's really the quantization once and for all. And the sort of like a Lord of the Rings, one ring rules all. So there's only one quantization to go through. You start with the Lagrangian for a field psi, you quantize it, and you get particles. And so this psi is really an annihilation operator of the particle. And so that distinction, I hope, is getting more and more clear. Okay, let me stop here again. So this is definitely not the Schrodinger equation. Any questions about that?
Oh, where did the factor of I, the second factor of I come from? Like psi dagger I, psi dot.
Psi dagger I, psi dot. Oh, this one here?
It's first. Yes.
Oh, yeah. I
Fact, psi
apologize.
factor of
This
I.
is a typo. There shouldn't be a factor of I. I should fix that later on. Thank you. So there is no factor of I here either. Yeah. Sorry about that. Any other questions?
Yeah,
Okay.
I have one also. Is there also a missing factor of psi dagger in the Euler-Lagrange where the UD is that? Or is that one just gone?
No,
as well?
I took the variation with respect to psi dagger.
Oh, right.
So
yeah.
I factored del
So-
psi dagger from all terms and factored it out. So this is what remains, which is supposed to multiply that variation. That's why I have only one psi dagger left. Thanks for the question.
Okay, yeah.
Anything else?
Oh,
Go
yeah,
ahead.
I had a quick question. So
Okay.
in the continuum limit, we take d to 0, but we're left with a factor of d in the self-interaction term. But since we took d to 0, how does this term not just go to 0 as well?
Yeah, so you have to assume that u goes to 1 over d in the continuum limit. So you go from discrete space to continuum space. So you need to decide what quantity gets fixed when you take the limit. So you need to take this product u times d fixed to take a proper continuum limit in this case. So it's sort of like delta function, right? So when you have a delta function, you start with like a box. And when you actually make the limit of this going to a really localized, then you have to make the peak higher, and eventually delta function goes to infinity. So that's the same idea I'm using in terms of taking the proper limit. Thanks for the question. Anything else? Okay, so what did we learn? So we'd like to do a basic recap of what we have done. So if I didn't follow through this heuristic discussion trying to build QFT, I could have done it top down. Namely, I tell you, believe me, this is the starting point. Whether you buy it or not, I could have done that too. And this one has everything built in now. So I have these two terms which describe the free particle. I have the third term that describes the external potential. And fourth term, so what I used to write u times d is now replaced by this Greek symbol lambda to describe the self-interaction. And I could have told you, believe me, this is how you start QFT. And at least in my case, that wouldn't convince me why I should take this seriously at all. And that's why I went the roundabout way of trying to build this one up. But at the end of the day, we derived it from quantum mechanics. So I should be able to go top down as well once I'm giving this Lagrangian what I'm supposed to do. The first thing, as I said, is to derive the canonical quantization condition. Psi is the variable. Again, this I should not be there as a typo. I apologize again. IH bar psi dagger is the canonical momentum. And I set up this canonical commutation relation between psi, which is the variable, and psi dagger is the momentum, and I cancel the IH bar from both sides of the equation. So this Lagrangian tells me this is the commutation relation. Then looking at this and say, aha, this really looks like psi is an annihilation operator, psi dagger is the creation operator. Then from this Lagrangian, I also derive the Hamiltonian. And so because this commutation relation suggests I'm looking at the annihilation and creation operators, I start with the vacuum state, which is annihilated by annihilation operator. And I start constructing these multi-particle states using the creation operator. Then I take arbitrary linear combination of these states with n particles using this capital psi. So what I'm left to do is to verify that this capital psi ends up following the same equation as the Schrodinger equation in quantum mechanics. And I also can identify what should be the number operator in this case, because psi dagger psi, it counts the number of particles at position x, you sum over x, which is of course an integral in the continuum. So this is the total number of particles in a given state. And the first thing you can verify by acting this operator on, let's say, this 2-particle state. I can commute psi with psi dagger twice. I get delta functions. I can integrate, and then I get indeed the eigenvalue 2, and you are going to actually do that in the next homework problem. So you can really see that this corresponds to 1-particle state, this corresponds to 2-particle state, this corresponds to 3-particle states, and so on, using this definition of the number operator. So that's a good start. So this state does describe n-particle state. So what remains to be seen is how this coefficient function, capital psi, would evolve in time. So that's what I'm going to actually do next. So any questions about this idea? So this is the recap. Now I'm going sort of backwards from my discussion. Most people take this as forward. What I have been doing so far is probably backwards because I was trying to build it up. But I hope the idea makes sense now that you know how this sort of makes sense from the point of view of building this theory. Any questions?
I have a question on the interaction term.
Okay, go ahead.
We're assuming that it's repulsive, but could it not be attractive?
Yeah, it can be attractive if you take the sign of this coefficient lambda to be negative. Right? Just like in the case of usual interaction, the repulsive potential is positive, attractive potential is negative. So that's encoded in the sign of this coefficient lambda.
Okay.
So you can take lambda to be negative to describe an attractive force among particles.
Okay, thanks.
Thank you for the question. Anything else? Okay, so what we're trying to do here is if you're given this Lagrangian for the field theory, I'd like to see the multi-particle quantum mechanics popping out of it. So that's the way now I'm trying to see the equivalence between the two. So let me start with 1-particle state. So I create 1 particle acting creation operator on the vacuum state. First thing is to verify is that it has indeed eigenvalue 1 for the number operator. Number operator defined on previous slide is psi dagger psi integral space. Again, just to avoid the clash of notation, I changed the dummy variable integral to y instead of x, so that this y looks different from this x, where the particle exists. And I play the same trick I did before by changing this psi y, psi dagger x by the commutator. I add a piece where psi is on the right, which acts directly on the vacuum state with no contribution to the end result. So changing this product to a commutator, I'm just adding 0. So I haven't changed anything. But given that this is the canonical commutation itself, that's actually the delta function. So I rewrite my delta function. Then I can perform y integral, and all the y's get replaced by x. So I recover the original state, psi dagger x, acting on the vacuum state. And comparing this left-hand side and right-hand side, I can identify the eigenvalue of the number operator is indeed 1. So this is the 1-particle state. And in general, an arbitrary 1-particle state is a linear superposition of the position eigenstates. And that's why we introduce this smearing with the weight function capital psi. So that's a linear combination of the position eigenstates. And because I'd like to finish, I'm going to the next slide and I can take questions after that. So once you have this state, then I can write the Schrodinger equation now in quantum field theory by using the same idea as in the quantum mechanics Schrodinger equation, except that Hamiltonian is now given in terms of the field. So what I'm supposed to do is to act the whole thing on this 1-particle state. And I will come back and show this again on Friday. So here I'm doing this very quickly. But the point here is that you can literally do it. So left-hand side of the Schrodinger equation is time derivative. And time dependence in the Schrodinger picture is only in this coefficient function capital psi. So the left-hand side gives you time derivative of this coefficient function. Hamiltonian acting on the state, and after doing some algebra, and we'll come back and do this together on Friday, so forgive me for now, ends up giving you this combination. And again, by doing integration by parts, I get this now the weight function capital psi with this thing acting on it. And by comparing the left-hand side of the equation, which is the time derivative of capital psi, which is now given in terms of minus h plus with 2m Laplacian on psi and potential times psi, which is precisely the Schrodinger equation for one particle state living in the external potential V. And I will show you explicitly on Friday that this self-interaction term does not contribute because there's no two particles that would interact. So I end up getting the Schrodinger equation for simply a one particle in the potential V. So that's the first time we're verifying that you are reproducing quantum mechanics. So we started out with quantum mechanics and built QFT, but now I'm starting with the QFT and re-deriving quantum mechanics. And you can go back and forth and therefore has identical physics contest. It's just a different description, different formulation, but the same physics. Okay, so that's what I keep showing. And I start with this slide on Friday, and I skip some of the derivation here. So we go through this one by one and much more slowly on Friday. Okay, so this is the end of my lecture today. Any questions about that? And I see one chat. I'm wondering if someone can please share the Discord link with, what is Discord link?
Oh yeah, sorry. Please disregard that.
Oh, okay, all right.
Oh, thank you, Usher.
Any questions?
I had a question.
Go ahead, Usher.
Do we have a different looking normalization constraint now for states with multiple particles?
Yeah, so I haven't so far talked about normalization at all. So you can talk about normalization by taking inner product of this state with another state with position y. And once again, you can work it out. It turns out to be delta function. So this does give you the correct delta function normalization of position eigenstates, just like we have seen in quantum mechanics. So even the normalization turns out to be in one-to-one correspondence, it turns out. Okay, thank you for the question, Asha. Anything else? I see another chat. Sorry, I missed the lecture today. When will it be posted on YouTube? Later today, this afternoon, I promise that. Anything else? Okay, so as I said, I go through this argument again on Friday because I kind of rushed towards the end. So you will see the whole thing once again, and I go much more slowly. So when you have questions then, of course, you're welcome to ask. All right, great. See you on Friday.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks.